Hello, good afternoon, and welcome to Think Science. I'm Nathan Cohn with Texas Public Radio. And at each of these Think Science events, our goal is to bring you in and out in just about an hour, having learned a little bit more about the topic at hand. And our focus today is on storm prediction over sea and land, and we're in the season for it here in Texas. Today's presentation is made possible by Geekdom and by you as a supporter of Texas Public Radio. Just yesterday, the National Atmospheric and Oceanic Administration, NOAA, released its predictions for the Atlantic hurricane season, and they're saying that this summer could be above normal, a 60% chance of such, with 13 to 20 named storms. Hurricane season begins June 1st and runs through November 30th, and as we've seen, some of the deadliest and most destructive storms can come late in the season, in August and September here in Texas when it really peaks. We've also had an unusual winter and spring in South Texas for those who have been here. At the end of April, we had a weather event that brought almost as much rain within 4 days as we normally receive for the entire year up to that point. And of course, there was the record-breaking snowfall that happened in February. So lots of stuff going on here in South Texas. Today, we're going to hear from three folks whose jobs and research intersect with weather and how predictions are made. We're going to hear from Jillian Redfern from Southwest Research Institute, Dr. Shuyi Chen from the University of Washington, and Dr. Harold Brooks from NOAA. Each of these great presenters will offer an overview of their work and research, and I know what they have to say will spur some great questions, which you'll be able to ask today as well. So when it comes time for the Q&A portion of our panel discussion this hour, I'd ask that you type your questions in the questions section that you'll see on the right side of your screen for GoToWebinar here. You could also use the chat room as well, but the questions section is where we're really going to look for those questions to come in. And as they come in during the Q&A portion, I'll relay them to the panelists along with some of my own follow-ups today. So we're going to hear from our first presenter today, who is Jillian Redfern. She's the Missions Operations Manager, or MOM, as she says, of NASA's Cygnus project, which launched in 2016 and has been extended through 2023. The Cygnus goal is to understand the coupling between ocean surface properties, moist atmospheric thermodynamics, radiation, and convective dynamics in the inner core of a tropical cyclone. So Jillian Redfern, thanks so much for your time today. Thanks for being here, and we're looking forward to hearing what Cygnus does and hearing your presentation.
All right, thank you so much, Nathan. Let me make sure I'm sharing my screen. Am I sharing my screen?
Yes, we can see your screen.
Oh, you can, okay. Hopefully you can see my slides. Let's see if I can move that over. You guys see my slides? Okay. Somehow I just see a picture of myself. All right, let me fix that in a second over here. Okay. All right, thank you. Yeah, so I'm going to be giving you a bit of an overview of Cygnus, which is the Cyclone Global Navigation Satellite System. Cygnus is composed of 8 microsatellites that are in orbit above the Earth that studies the intensification of tropical cyclones. If I can get it to advance, I apologize. There we go. Yeah, so prior to Cygnus's launch, you know, obviously we were able to track tropical cyclone forecasts as well as try and understand the intensity of those tropical cyclones. But previous spacecraft measurements were attenuated by rain, which obviously if you're trying to look underneath a hurricane is slightly problematic. So currently, the way it would work is we would fly P3 hurricane hunters that NOAA flies to study the intensity measurements. And so they would basically fly through a hurricane with an aircraft and drop sensors into the actual hurricane. That obviously puts personnel in a bit of a picky wick when they're flying through a hurricane, and that can be slightly dangerous. So the 8 Cygnus spacecraft that launched in 2016 are able to provide gap-free coverage for 24 hours every day. And we do have a storm revisit time of 6 hours. So the way Cygnus works is signals are sent down from the GPS satellite and are reflected off of the Earth and come back up to the Cygnus spacecraft. And so we kind of work the way your eye works when you're looking at a lake. So when the lake is calm, basically you see the moon reflected almost perfectly in the water. But when there's wind over the lake or over the ocean, you start having some waves. And so instead you get a much bigger specular point, a much bigger glistening zone. And Cygnus can detect that. We're also getting the direct signal from the GPS satellites onto our spacecraft as well. And so this is what one of our delayed Doppler maps looks like. And so essentially the shape of this arc here shows you how much wider that reflectance is when there is a lot of, quote unquote, wind noise or wave noise going on in the water. So here's a nice movie that we can see of all of the different Cygnus spacecraft flying over the Gulf of Mexico, as well as the Caribbean and the Atlantic, as Harvey is approaching Texas. As you can see here, we fly over quite a bit as the storm was approaching, and we're able to get really great data on that. So you'll notice that, Harvey's getting closer and closer. And then one of the really awesome things that Cygnus has been able to do is look at soil moisture. So over on the right of the screen, you can see what the signal to noise ratio looked like prior to Harvey hitting. And then looking down below, once Harvey has hit on the 27th, 28th of August of 2017, you'll see that we're starting to pick up more noise here. And so basically that means that the soil is moister as Harvey is leaving a flood. And then, starting on the 30th, Harvey has moved on more towards Louisiana. And at that point, some of the water is receding away from Houston. And so we're able to see that as well. So I just wanted to quickly thank the Cygnus project team. So our PI is at the University of Michigan. That is also where the Science Operations Center is located. The Mission Operations Center is located in Boulder, Colorado. And then we also, down at Southwest Research Institute in San Antonio, Texas, that was where we built all 8 of these spacecraft. So I just want to say thank you to everyone. So thank you, Nathan. And I will stop sharing.
Jillian, a real quick question here. One thing that you showed right there towards the end was that in addition to being able to better track the storm as it moves, you showed moisture on the ground, that Cygnus was helping to identify that, which basically means that you're mapping flooding as well with Cygnus. Is that something that can be used in the future for better identification of flood zones and flood control?
Yes, most definitely. Yeah, we've since we launched, our main mission was to study tropical cyclones, but since we constantly take data, over land and over ocean, we've been able to notice that Cygnus actually has a few more tricks in its bag. So we've been looking at soil moisture, we've been looking at river slope, we've also been studying the freezing and thawing of high altitude lakes over Tibet. We've also been doing some studies of lakes so that we can basically differentiate the difference between land and water. So there's lots of really exciting new experiments and new science coming out of Cygnus.
Well, that kind of dovetails into something that I think Dr. Chen is going to addressed partially in her presentation as well. So let me go ahead and welcome her. Dr. Shuyi Chin is a professor of meteorology at the University of Washington's School of Atmospheric Sciences, and her research interests involve observation of how the atmosphere and ocean interact with hurricanes and typhoons in tropical areas, and the use of mathematical models to predict weather patterns. And during the 2005 hurricane season, Chin monitored Hurricanes Rita and Katrina and Wilma aboard Doppler-equipped aircraft to help create stronger hurricane prediction models. Thank you, Dr. Chin, for your time today. Thanks for being here, and we're looking forward to learning from you.
Yeah, thank you. I'm very glad to be here. Can you see my screen?
Yes, we can.
Right. So my next 5 to 10 minutes is going to be focused on the how we are doing hurricane research and looking into the next generation forecasting models. So my own research deal with tropical cyclone observation from both aircraft and the satellite data, and also building computer model that have both atmosphere and ocean and surface waves. So I'll introduce you to those product and using Hurricane Harvey as example. So the picture you're looking at on the screen right now is a picture taken inside of an eye of Hurricane Katrina in 2005. So we had a research program called RENEX. We've flown 3 different research aircraft. This is happened to be one of the missions that when Katrina was in the Gulf, reaching its peak maximum. And inside of hurricane, usually you see this eye wall kind of tilted upwards. And then there's kind of a rotational appearance there. And it's really beautiful inside. But then on the other side, hurricane impact usually is very devastating on the ground. So that kind of a nature has this power in terms of developing such beautiful system, but on the other hand, it can be very, very devastating in terms of a damage. So with that, I'm going to start with how the current forecasts that you're familiar with, then move to introduce our next generation coupled model in the research mode. So this is the figures you guys, everyone familiar with is Hurricane Harvey's forecast by National Hurricane Center. The picture on the left is a satellite image showing Harvey right before the landfall with very clear eye. And that is the one that, if you can think of the picture I just showed before, the aircraft fly inside of these hurricane eyes, and we can actually taking data, understand what is driving the intensity and how the structure of the storm, that we can understand storm in terms of helping for the prediction problem. And in current hurricane forecast you're familiar with is that a Hurricane Center will issue hurricane forecast in terms of where hurricane's gonna go and how strong the hurricane is. So this is a cone of uncertainty that you're familiar with, and that the intensity is by far the most challenging part of a forecasting problem. So in this figure, as you probably can see, it's hours lead time. So this forecast was issued 3 days before Hurricane Harvey making landfall on the 23rd, Wednesday evening. And that storm, actual storm, is plotted here in terms of observations later on, that rapidly intensified into a Category 4 major hurricanes. But during the time of forecast, that computer models has difficulty to intensify that storm. So basically Hurricane Center forecast still calling for a tropical storm. Only 1 day later that we start catching on to see that storm become a major hurricane right before landfall. And then as you can see, the forecast started catching up with the actual observations in about 2 days lead time. So that tells you that forecasting these rapid intensification is still very difficult. And this is particularly important in the Gulf, because Gulf of Mexico, most storm, when they form there, they're going to make landfall somewhere. So this is going to have a very, very large impact in terms of a societal, economic, and also human lives. So this is where my research has been focused for recent years, that we're looking at how hurricane impact in society when it's making landfall. So as you can see, these pictures tells you that, as you would recall, major hurricane like a Katrina, when it's making landfall at category 3 intensity, but at the same time, lots of flooding that has something to do with infrastructure as well. So the levee break, and we have quite a bit of devastating effect. And then hurricane also have effect on strong winds, and then destroy a lot of the houses and the infrastructure as well. On the other side, there's another well-known storm, Superstorm Sandy. Even though Sandy, when it makes a landfall near New York, New Jersey coast, the category in terms of intensity is not as intense. It's only category 1, but it made huge impact, not because the wind itself, but a storm surge. So flooded Manhattan subway system, and as we all know how much damage that done. And also dumped over a foot of snow in West Virginia. So as you can see, these kind of storm impact could be very complex, more than just to say where it's going to make a landfall and how strong of the peak wind is. On the ground, there's much more to that. So what we do in the research community, my graduate students, postdoc, and working with many research scientists, that we're building computer model to represent the rainfall and the storm surge and ocean properties, all in this model that we can better represent the totality of hurricane impact. So let's start with a movie that's showing this coupled model forecast. So as you see, these this is a path of a Hurricane Harvey, and where the center is indicated by that hurricane symbol. And this is a very complex storm, as you know, first intensified over the Gulf and make landfall in the Texas coast, but then it came out of the Gulf over the water again, and then making a second landfall over northeast part of the state. And this is a time that you can see the ocean, the color part is the ocean's sea level height anomaly. So if you see the color is red, representing the elevated ocean surface, so that represents the storm surge. So usually when we think of a hurricane making landfall, we're thinking a lot of wind, but at the same time, the storm surge can be a very devastating effect, and it can be complex. So as you can see, the elevated sea level along the Texas coast, it's much larger than hurricane footprint itself. That because we have onshore flow, like indicated by the vector, and the perpetual pushing the high surface waves and also water to that. That created an environment that itself may not impact the Houston area directly, but has this impact of a blocking drainage out to the sea. So that's the hurricane forecast model that we can actually represent in both the rain and the storm location, and also the storm surge properties this is over 7 days forecast. So pretty much, as you recall, Hurricane Harvey thing is not just rain, it's really just a flooding part. The flooding itself has several different important factors affecting that. It comes from the rain, a lot of water. At the same time, we do have storm surge. Another important part is how the water gets drained. So if you have a very good drainage, then you have reduced the possibility of building up a very bad flooding situation. But happen to be in Houston area, as you see and recall, in this area, we have flooding partially because the building environment that has all the concrete that has very poor drainage into the ground. At the same time, because the blockage of the sea, because water come on shore, then it blocked the drainage to the sea as well. So if you're looking at this time series that forecasts the storm surge, this is observed surge on a tide gauge station. That tells you that over 7 days, we're perpetually pushing this storm surge water in this region. Also model predicted that. So even though the storm surge itself is not very high, it's close to be about a couple of feet, but it blocked the drainage of water out to sea. So as these combination of the properties, that contributed this huge cumulative rainfall and flooding. And this is sort of a model forecast over that 7 days. So that tells us that the future model, and currently already in the research community and on its way moving to NOAA, contributing to the forecast in the operational, NOAA is also building something similar to these models that we can focus on the forecast of impact itself on the ground. But the grand challenge in the future still is that we have limited observation over the ocean. Our model are not quite high enough resolution, sophisticated enough in the operational framework that we'll continue to improving them. On the other hand, we are living in a rapidly changing climate with rising seas. Those coastal impact are going to only increase because that with the sea level rises, we don't really need it to be very strong storms in order to get the level of flooding. So in that case, in the future, in the risk decision making stuff would be benefited by these forecasting model. So with that, I'll stop here.
Thank you, Dr. Chen. A quick question about the forecasting of hurricanes before we hear from Dr. Brooks, and then open it up to questions from all. And so I want to remind folks that if you have a question, please type it in the questions box. Just a few moments ago, you talked about how the intensity was the most challenging part of the forecast of hurricanes. Why is that? Why is it so hard to? Why is that a difficult thing to forecast when it comes to hurricanes? Is predicting how strong they're going to be?
That's a very good question. So the hurricane movement, where they go, we call the hurricane track, is controlled by the large scale environment we call the steering flow. So that is where large scale circulation surrounding it's pushing it, right? So that part of the atmosphere that is much better observed and resolved by our computer models. Computer model have a grade. So then, if a grade is like, say, 10 miles, or you can think of a 15-kilometer, that's an operational model, then they can actually resolve the large scale system over thousands of miles and things, right? However, hurricane intensity, it depends on these structures, as these are very smaller scale, and how strong of the convection storms inside the storm. So like the one that I show you in this picture, the Hurricane Katrina. So this is only 10 to 20 miles. That computer doesn't have quite the resolution. And also we have observational issues. We don't have a very high resolution observing them. So in that case, the representation of a hurricane itself is not quite adequate yet. So then forecasting this, how intense the storm, depending how much we can actually resolve in our computer model. So we're still improving it. In the current situation, it's still very difficult problem to predict.
I see. Okay. Well, let's move on and hear from Dr. Brooks, and then we'll open it up to all for questions here. Dr. Harold Brooks is a senior research scientist at NOAA's National Severe Storms Laboratory, where he spent 20 years on the climatology of severe thunderstorms and tornadoes, forecast evaluation, and the interface between social science and weather. And Dr. Brooks, thank you for your time today very much. I'm looking forward to hearing about your work at NOAA.
Sure. Okay, and I think I just clicked the wrong spot and killed my sharing of the screen, so I need to figure out how to do that if I can.
Okay.
There we go. I think, okay, let me.
I see your screen.
What's it doing? You see my screen, so you see pictures of me?
I see
okay,
a sand dune, your desktop.
A sand dune, that's really exciting. That's really exciting.
Here's your PowerPoint.
So I think
it looks like.
Yeah, and I just killed it. I'm being a okay. So that for background for everybody, some of you may know that we had a hailstorm in Norman a couple of weeks ago, and my house is getting worked on right now.
Wow.
And so there's a lot of distractions happening outside my window. Okay, so hopefully I can avoid those. Okay, and now do I need to? Are you getting the? We're getting there. Okay.
Yeah.
So are you seeing my screen or the presenter mode?
There it is. I see forecasting and understanding severe thunderstorms.
Okay, but is it the screen or is it the presenter mode?
It looks like it says slide 1 of 11 down there below it. And
okay, so okay, so that's that I want. Okay, yeah. Now you should just have the regular screen on. Okay, so talking a little bit about forecasting and understanding of severe thunderstorms, and this is as Nathan mentioned, I've been working on this for quite a while, and I really want to try to think when we think about how we understand storms. We have a couple of and this is both for understanding what's going on and for forecasting. We have a couple of sources of information, and one of our first sets have to do with the reports that we see out of severe weather, of tornado, hail, and wind. And in the United States, severe thunderstorms are defined as being either a tornado, being hail of at least 1 inch in diameter, or being a wind gust of at least 50 knots, which is 58 miles an hour. And the wind and the hail actually goes back to training aircraft for the Air Force in the late 1940s was what led to those, and we still have them around. It's important to remember, though, that reports are irregularly collected, and they're there to collect it to verify warnings. They aren't really collected to give us a full understanding of what's going on, and that turns out to be really important. So we have to be really careful about how we use them. As a nice rule of thumb, there are approximately 500 EF1 tornadoes or stronger in the United States each year. And there's really no trend in that over the last, say, 60 or 70 years. Lots of other, if you make the threshold at any other level, there have been lots of things that have happened to change the way we collect the reports. And so that's a baseline number of roughly 500 as a rule of thumb. We also use the environmental conditions a lot. We can estimate the occurrence of storms based on the ingredients needed for weather. We can use those environmental conditions if we wanted to drive high resolution simulation models that'll help us look at things. These environmental conditions work. That drives, as I'll show in a bit, that does both how we understand the climate setting and therefore the climate change setting of severe thunderstorms, and how we understand how to make forecasts. And so what's changed over the years in severe weather? I think that's one of those things that people say lots of things about storms, and so a lot of it's based on not the best use of the data. But one thing that we're really confident in is that, in fact, variability of tornado occurrence has changed a lot in the United States. This is a plot that shows the number of days per year with at least one EF1 tornado in the blue, and like basically a decadal average in the darker blue lines showing the long-term trend. And then the number of days per year with at least 30 F1 tornadoes in the red colors, same plot. You can see that in the 1970s we averaged about 150 days per year with at least one tornado, EF1 tornado occurring on it. And that number is now down to around 100. But at the same time, the number of days per year with at least 30 has increased from being roughly half a day per year, so 1 day every 2 years, to being 2.5 days per year. And that's occurred even in years where we haven't had very many tornadoes occurring. We've still had that number of days with lots of tornadoes occurring. And remember, this is all in the context of having the same number of total EF1 tornadoes taking place in the country. And so fewer days with a tornado, but more days with lots of tornadoes occurring on them. And people ask the question, well, what's the impact of warming temperatures? As we warm, will be more tornadoes, more severe weather, or not? Tornadoes are actually relatively complicated. If we look at the national numbers, this is a plot that shows what the impact of having warmer than normal temperatures, and the temperatures and the warmer than normal temperatures and the number of tornadoes that occur. And in the wintertime in the United States, if we are warmer than normal in the wintertime, we have more tornadoes than we would in a normal year. But at the same time, if we're warmer than normal in the summertime, we actually have fewer tornadoes in the United States. And so there's a balance between, these two things are changing, so that just by automatically changing the number or the temperature, we don't really know whether they'll, on the annual basis, it's hard to tell the impact of temperature in the U.S. on the number of tornadoes, but we have a really strong seasonal signal that takes place. And one of the important things about this is that the wintertime tornadoes tend to take place in the southeast United States, and the summertime tornadoes tend to take place in the northern plains. And one of the big differences we see there is the impact on society. That there are a lot more people who live in the southeast, particularly in rural areas, than there are in the northern plains. So an increase in tornadoes in the wintertime will tend to have more of a societal impact than the decrease in tornadoes in the wintertime. We're still trying to understand everything that goes into this. So what are the ingredients we look at for storms? We look at having warm moisture at low levels and relatively cool, dry air aloft, and that's related to the energy that's available to make the storm go up and hold hail up and produce really heavy rainfall. We also look for a change in the horizontal winds with height. It's the wind shear term that leads to how the storms get organized. If the parent storm is organizing. One of the real reasons why the central part of the United States gets so many severe storms is that when we have winds out of the south at low levels, that's bringing in the moist air off of the Gulf of Mexico, and winds aloft from the west, that's bringing it over the Rocky Mountains, over the high desert of the southwest, which means the air is relatively dry aloft, and that brings in so when we have those winds in the right directions and increasing in speed with height, we bring in the right thermodynamic properties. So the ingredients come together here more than any other place. When we look at the ingredients, we can actually look at the distribution of how likely are we to have severe storms given a combination of ingredients. And these are now the wind shear term on the vertical and a measure of the energy term on the horizontal axis. The gray is where the overall distribution of environments that we see in the U.S. And so most of the time we're down in the low wind shear, low energy thing where interesting weather really doesn't happen very much. The red indicates the probability of having severe weather given that we have that environmental condition going on, and it increases rapidly up to the high wind shear and high energy term, and it gets cut off here not because necessarily when we get there that severe storms won't happen. It's just we don't go to those environments often enough that we can actually make good estimates of what the probability is. But that we can also then, if we go a step further, as a little cartoon, we actually know that tornado and hail in particular like to have lots of wind shear, and so tornadic and hail storms tend to occur when there's lots of wind or lots of wind shear, and non-tornadic winds tend to occur more often when there is lower values of wind shear. And so this allows us to make a really crude, simple estimate of what will occur forecasting-wise, and forecasting efforts actually go into a lot more sophistication on the details of this. But this also allows us to make crude estimates of where we would expect to see storms, how we would expect to see storms change in the future, and using something really simple is just essentially looking at where the red contours are. We can actually make estimates of where we'd expect to see severe thunderstorms in anywhere on the planet. And the two biggest areas are the central part of North America, and then the east of the Andes in South America. Probably northern Argentina probably gets the largest hail on the planet. The central part of the U.S. is a close second to that kind of an effort. And then other areas that sort of, if you look at geography, tend to be downstream of mountain ranges or plateau regions or deserts, and poleward of bodies of water that can provide the warm moisture. But this real simple, crude thing allows us to do a lot of different things. We can actually use that same kind of a thing, adding in now all the other things that go into making forecasts and looking at reports to see how we would expect to see how tornadoes have changed in the past. And this is over the last 40 years. The left side is simply a count of the reports put onto a grid, how they've changed over the years. And the right side is how the favorable ingredients for storms have changed. And they look relatively alike if your eyesight isn't perfect. And so this actually allows us to get some idea that that what we've seen in the reports over the last half century is not just a case of changes in the way we collect the reports. It actually is associated with the environments. Now, as a point of caution for everybody, especially people who are living in Texas that might see this and go, things are not happening as much. The changes we're looking at are still relatively small for an individual. These are changes that may be changing the frequency by 10% of events up and down over the course of the 40 years. And so that would be, an event has gone from being a 10-year event has gone to being a 1 in 9 or a 1 in 11-year event. And you really shouldn't be making safety decisions based on that. Real brief overview then of some current forecasting practice, especially prior to the warning stage. We look at ingredients to do two big things. We look at convective outlooks that are produced out to 8 days in advance to say that severe storms are likely to occur in certain places, and then the ingredients also factor heavily into the watch decision that's made. These are all both made by the National the Storm Prediction Center, which is a national center located in Norman. And watches will also include, have storms started to initiate? So that given that the ingredients are right for a storm to produce something, this is now saying that storms actually will be occurring. And observed storms are primarily based on radar, and this takes place in 120 forecast offices roughly around the United States. There's in Texas, there's Houston, New Braunfels, San Angelo, Fort Worth, Midland, Amarillo, and El Paso are the offices that warn for the state of Texas. And a convective outlook has a map that looks like this. This is a categorical look at it, going up from a marginal to slight risk to enhanced slight to moderate to high risk. This is actually for today. And so both you and I, or most of the audience, will be in a fairly clear area. There's a little bit of a chance of storms in western Nebraska. This is a forecast of the aerial coverage of severe storms. It doesn't say anything at all about the intensity. And then later on, and those are issued out to 8 days in advance. And then later on, the next thing that happens is there are watches issued. This is a watch that, at least for some people in Texas, should be a reasonably memorable one. This was associated with the storms that eventually produced the giant hail just west of San Antonio a few weeks ago, and this was the watch box is this orange, or is this pink shaped outline. It starts as a parallelogram and gets adopted to look at the county boundaries, and then this was the initial radar. And so this was issued at 3 o'clock in the afternoon for the storms that eventually got to San Antonio about 5 or 6 hours later. And these are the kind of products that we would use. These are looking at ingredients and the beginning of storms. And then for warnings, you would actually look specifically at the individual radar images to decide when the warnings are coming out. And again, that comes out from a local forecast office. I don't have a good image of that today, but we care about we're always working on trying to understand better how reports relate to reality. and how environments relate to the occurrence or non-occurrence of storms. And we've been working on and improving then our understanding both of what happens today, how far we can extend out the forecasting, and what will happen with climate change. And that should be all that I have.
Thank you so much, Dr. Brooks. Quick follow-up here. You mentioned that a few moments ago that the time for reporting a watch for an area, particular area, is about 6 hours. When I was growing up, of course, you know, a tornado warning was issued when somebody spotted a funnel cloud, right? And now you can use Doppler radar and things in order to measure the rain horizontally, I guess, in the atmosphere. What's the time now that you can issue warnings?
Okay, well, warnings are on average if a warning is issued prior to a tornado occurring. So we just take those cases, not looking at the cases where, for whatever reason, we didn't get a warning out in advance. Warnings come out on average about 13 minutes prior to the tornado. And it's important, okay, the watch stage is essentially, to me, I always think of that as you ought to be paying attention and making sure you're able to get weather information. You don't have to take any really specific action. Maybe you decide, maybe we won't go have the picnic. You know, I'll stay in this evening. But then, and you make sure you're able to get local weather information. The warning stage is now you should be taking protective action. This is now you should have identified during the watch stage, where am I going? If a storm threatens me, and what will I do? And then when the warning comes out, you take that action. And warnings are in effect for on average of, I think, a little bit less than 40 minutes currently in the United States.
That map you placed up was of the entire world. Also, was fascinating to me. You know, here's where all the areas are that are, you know, in some ways you could say are similar to what we have. And what is it down? What is the confluence down in South America that makes it kind of like us?
Well, South America has the Andes Mountains on the west, and so you bring the air just like bringing air over the Rockies. You know, that's the way we get the cool, dry air aloft. It isn't as wide as the Rockies, and so it tends to not behave exactly the same. Their source of moisture is actually the Amazon basin, and so they don't get their water off of the Atlantic Ocean. They actually get it out of the Amazon, and the reason they don't get quite as much, perhaps in total, as we do, is that the Amazon isn't quite as reliable as the Gulf is, because it is land instead of water, and the fact that the Andes aren't as wide. But when the ingredients do come together, they come together in absolutely spectacular ways. They'll get, you know, they get 5 to 6 inch diameter hail at a greater frequency than we do in the United States.
Wow.
Yeah.
We have about 15 minutes before 1 o'clock, and so if people have questions, please go ahead and type them in the question section here. Christine writes, Dr. Brooks, by the way, she says, I live near the approach to the San Antonio airport, and there's lots of vortex there. Could this contribute to an increase of tornadoes? Probably not. The scale that we're looking at, the way that rotation forms in storms that makes tornadoes is essentially we're tilting that change of the wind with height. You can imagine if you had a spiraling football and you tilt it on its side, that gets us rotation aloft, and then the rotation at the ground comes from the evaporation of rain as the storm wraps some rain around its backside, and that's a really large scale process. The things that we see, like with vortices and like with any transportation, aviation or automobiles, is just on such a small scale compared to what storms do, that it really doesn't have much of an effect. Dr. Chen, Jillian, if you want to put your cameras on too, just in case we have questions for all, I would follow up with a question that's open for anybody here as well, which is basically that, I mean, we've talked a lot about short range forecasting and long range forecasting today as well, and I want to know if are public officials paying enough attention to the long range forecasts being offered by NOAA and other agencies to prepare their communities for the future? This is an opinion question.
Yeah, so maybe I can sort of start this conversation. It's a complex question. It's a very good one. So as you probably refer as long-term, there's kind of projection for the future, how our community should respond to the current way of thinking that in a warming climate and rising seas. That's one way to think of that. And the other is the immediate one, that is storm like 7 days from now or 5 days from now, what we do. So hurricanes, for instance, has a very different way of thinking decision making, because like Dr. Bruce says, like warning can be say 13 minutes for tornadoes, then you decide to go to a basement, right? So there are things like that you can do. But in hurricanes flooding, it's much more expensive proposition. So for people to evacuate 3 to 4 days ahead, and that requires quite more sort of influence on their effect on their life. People have to leave their home and moving to a place where they can stay. So this really bring us to this: how accurate forecast can we have? If we have 7-day projection or 4 days, have enough time for people to act, but at the same time the uncertainty is very large. So then how do we act that maybe a false alarm sometimes, right? So there's a false alarm damaging things. So in the sense right now, we're all learning how to make this forecast more accurate in a little longer range, but then at the same time try to make sure we understand how people's thinking, the decision-making part, individually or collectively as a community. That's one way to think of this sort of how forecast will be used for that. But for much longer time scale, say certain region like in Florida, sea level rise is very much more than climate projection so far. In reality, we're actually seeing quite a bit that. So then that requires the cities and the states to really start to think about the infrastructure and how we actually build our community in this very much prone sea level rise region. And that's much more complex decision-making process. It requires a lot of a strong will from the political systems to, general public. So hopefully that's gave you something that we can have that conversation.
Dr. Brooks, you want to weigh in at all?
Sure. I think one of the things, on the projection scale that Dr. Chen talked about, we really aren't as sure about tornadoes and severe thunderstorms. I think we've got a pretty good hint that variability will increase, but I'm not completely sure how you respond to that. The biggest thing we really need to do is building resiliency on an individual and on a societal level. For instance, I said, I've gotten a new roof this week. My roof has much better shingles than the roof that was on there before, and better underlayment and all that other stuff. And just making those kinds of things a stronger option. And I'm hoping my insurance company gives me a little bit of a break for having they aren't going to replace the roof again. But that those kinds of things and making those incentives available for tornado protection, just it costs about 2% of the house value to dramatically improve performance in wind. And so when we do new construction, you should always be putting on hurricane clips and straps and all these other things that will help your house survive at a much higher level. And in the long term, the cost is, the benefits far outweigh the cost. But at the moment, we essentially, we right now as a society, we transfer that risk and that cost to the individual. And I think about, well, do I want to pay an extra couple of $1,000s on my house, or would I rather have, a nicer kitchen? One of those things that you have to think about. Whereas if they said, hey, essentially that's free to make your house survive and not fall apart, well, I'm much more likely to do that as a person. I think that's one of our real challenges, is trying to get that understanding of providing better incentives for people to become more resilient, having communities become more resilient.
Question about hurricanes and intensity. Most people know that the warm Gulf water intensifies hurricanes, but what are the weather patterns that lead to greater numbers of hurricanes in the first place? I'm thinking about the La Nina and El Nino weather patterns.
So, Julian, you want to chime in or?
So I'm an engineer, so I fly the spacecraft, so I can tell you about how the spacecraft work, but what leads to the hurricanes forming over the Atlantic. I know there's something to do with Saharan dust. I know that tends to churn some things up, but maybe Dr. Brooks.
Right. So hurricane, it's complicated in two different ways. One is where do they form? And after they form, where do they go? So then the variability of atmosphere conditions control them have lots of different ways to do that. So there's certainly El Nino, La Nina that we all know that can contribute to storm formation. So even though Gulf water is warm, however, if the atmosphere conditions has a very strong shear, as you probably often hear, that probably unfavorable for hurricane formations. So this is where the study focus on a lot of these future projections of climate change. So does these environmental conditions in the atmosphere that are also going to the same direction or opposite direction? So right, that's created a very complicated way of thinking this. There's another thing is the where storm goes. So in the way that there's another phenomenon called the NAO, the North Atlantic Oscillation, that controls large pressure system over the Atlantic Ocean. And that actually controls this where the storm goes when they form. Mm-hmm. So that changes every 10 to 15 years. So occasionally you probably see storms in certain decades were really busy. Some other decades are not as busy. So you can think of it, 2005, around those 2004, and those years extremely busy in the Gulf region. That has something to do with that pattern, that where the storm formed and where they're steering. So the El Nino La Nina one, that is every 2 to 7 years. So you start to put all these things together, you start seeing individual storms are going to be really difficult, right? Because you can see them as group favorable in some ways, but then individually it's different. So I'll give you one example that Hurricane Andrew hit Florida. That was 1992. And that year was the year of supposed to be unfavorable environment. It's a new year. So it turned out we have a very late season, right? Andrew in late August, the storm giving you that thing. But turned out that even though if we use a large scale projection, it's not favorable, but you get one of the strongest storm in that season. So as impact forecast, individual storm trumps everything else, if that helps.
Yeah, and I think that as Dr. Shen mentioned, the impact is always an issue. That it only takes one bad storm to make a bad year, and that's true in the hurricane world. That's true in the tornado world. That and that if Andrew, instead of hitting the coast, curves up the east of the East Coast, it affects nothing but the ocean, and we might not even remember 1992 as being an interesting year at all. And that's one of our real challenges is projecting paths in the future.
Question here from Derwood, who asks, well, you have two questions. First, we'll ask one more hurricane question, and then I have a tornado question from him. The hurricane question is, what do you believe is the chief cause of the increased intensity of recent hurricanes?
The recent hurricanes, it's some attribution. So people do study attribution, and it certainly have a lot to do with the warm oceans. Warm ocean not only provide thermal energy and also provide moisture. So if we have the same dynamic factors like winds and things, then the storm will be more intense. Just given the warm ocean, you'll get more energy out of that. But then at the same time, for projections that whether we'll continue to have this or not, the jury is still out in terms of a climate projection part of hurricane work.
And his tornado question is, and this is something that I've talked about with my wife too, is, so Dr. Brooks, why don't tornadoes occur in major metropolitan areas as much?
They do. The major metropolitan areas are small, area-wise. If you, we've got lots of tornadoes that have hit metropolitan areas. It's just that, if you took any area of the country comparable to cities, you wouldn't think they got hit very often either. It's just they really aren't very big compared to the rest of the country. But certainly in the last 30 years, we've had tornadoes in Dallas and Fort Worth, in Nashville a couple of times, Birmingham, Oklahoma City, St. Louis. They happen. Cities aren't very big. Is the bottom line.
So it's really more just perception.
It's a perception, yeah. It's a perception thing. It's if you and we you think if you there are places that have that tornadoes, if you come close to it. We actually did a study last year where we looked at essentially near misses of metropolitan areas, and that's one of the actual interesting questions is as suburb sprawl. Mm-hmm. We call it the increasing bullseye effect. That we've had enough events that have occurred that have been close, and all it takes, as I said, all it takes is that one bad event, and it's a bad year. And so if you move a tornado by a few miles, which in the atmosphere doesn't really care, because the cities don't really matter that much on the scale of the thunderstorm. But that it, you move even something like the Moore, Oklahoma tornado of 1999 or 2013, you move it by 5 miles either direction, and you have dramatically different impacts. Yeah. Both depending on which direction you go, more or less.
True.
Depending on exactly where it goes. So.
Well, we are just about at the top, so I have one last question, which is a silly question, which is, have you ever picked up the Old Farmer's Almanac, and has it ever been right?
Well, yes, indeed, I have. And the great thing about the Farmer's Almanac is their forecasts are written over such a large area and written so vaguely. If one of their regions is, and I get confused between the Old Farmer's Almanac and the Farmer's Almanac. I admit I get confused. They are. One of the areas is most of Texas and Oklahoma. Yeah. And you'll read a forecast, it'll say something like cold over a week-long period, cold and rainy. Well, over that size of a region, that's going to happen to someplace all the time, and so you can always call the forecast right. And people have actually done studies of it, and that's pretty much what it comes down to. Is if you make your forecast vague enough and over a large enough area, anything works.
Fantastic. Well, thank you all for being here today. Jillian Redfern from Southwest Research Institute, Dr. Shuyi Chen, professor at University of Washington, Dr. Harold Brooks of NOAA. Thank you very much for your time today. I sure have enjoyed learning. And I want to remind everybody that this presentation will be archived and placed on our website and up on Texas Public Radio's YouTube channel so that you can share it with your friends and colleagues as well. I want to thank Geekdom for their support of Think Science, and our next Think Science discussion will be coming up in August. We'll be talking about space exploration and heading out to new frontiers during that time. So I'm Nathan Cohn. Stay safe. Keep wearing your mask for safety if you need to, and we will see you very soon. Thank you all for being a part of this.
Thank you.
Thank you. Thank you.